this sentence means. So if you remember, we said if we have, I'm going to write it up here. If we have a class and we have an abstract class and we're going to inherit, or we have two classes, and one class is going to inherit, class A is going to inherit from class B. Between these two, we have to extend, right? So class B, A extending class B means it's going to inherit everything that we have in the class B. We can also, class A can implement the interface C, for example, right? So we need to use the keyword implement. Implement. Oh my God. I need to use keyword implement. So from the class to interface, from the class to class extend keyword, class to interface is going to be interface keyword. Can we do interface that somehow inherit from another interface? Can we do that? And the answer is yes. For interfaces to inherit from each other, you need to use the extend keyword again. So comparable is an interface, and I want to tell that E, whatever the type of E is, it has to be a kind or a type of a comparable object, so I can basically, so this is just a side note, right? So it just had nothing to do with what we're going to say, but there is a class of type or object of type E, and when you want it to be a comparable object, so it has to extend the comparable interface, so, and with the same type, so we can have the compare to method. So comparable interface has a compare to method. So let's look at the code for the comparable interface. So as you can see, comparable interface has only one single method in it, and that's compare to. And it's getting an object of type T, whatever the generic type is, and is going to return an integer type. So what are those integers? So if it's a positive number, that's telling us that basically the our objects is going to be bigger than the objects that we're trying to compare with it. It's a negative object, is going to do it opposite way. So you can read the description of it, right? So the result is that it's a positive number, negative number is 0. And so that's what it's going to be returned. So which objects are going to be comparable? Every objects in the Java library, string, integer, all of those basically provided objects in Java library, they're all comparable. So that means if I have a tree of type string, or I have a tree of type integer, or a tree of type of any number, that part of the number class, they're inherit from number class, they're all going to be comparable as well. But if I'm trying to create an array list or a rule, a binary search tree of type circle, I have to make sure my circle is a comparable interface. Otherwise, it won't let me to even create this binary search tree for it. So first, I have to go to the circle, and circle has to first implement this interface comparable. That means it has to implement the compare to method of it. And then I can use that compare to method inside my binary search tree, so I can create I can use that. So the question is why we need to do that, and the answer for that is that why not equals? Because equals are only going to return true or false. Here we don't want to just do true or false. We want to know which one is bigger, because we either have to go to the left or right, and in order to know we have to go to the left or we have to go to the right, we need to know which one is bigger. And in order for me to understand that, I need to use the compare to basically method. So how we're going to use that, the elements is going to have the compare to method, and I'm going to compare that with the current dot, same thing that we had here, the current dot element. So it's going to return either a, this is going to either return true negative, no, less than or bigger than, right? So it's not returning equal. So I have to now do the checking. So if it's a negative value, then I know the element is less, and that means I have to go to the left. If this returning a positive value, then I have to go to the right. And otherwise, I know that they're basically zero, right? So it's either of those three, you know. So it's either negative, positive, or true. So that's why we're going to implement it this way, basically. So this is our while loop. After we're done with this while loop, there are two scenarios can happen. Either our parent is saying null, and that means the node, we find a node, but it doesn't have any parent. That means that's a root, right? So that means that we're adding things to the root. So we have to kind of keep that in mind that, at this point, the value of what is going to be the value of the parents. If you want to use the value of the parent, or because if you have two options. You could do this also from the beginning, starting from the root, because we know for sure that the root itself is not empty. So I could do that, or now we keep it as null. So if I keep it as a null, then I have to make sure that here I basically maintain the value of it, right? So I have to know what is the parent. So parent cannot be null. If the parent is null, then I have to use the children. So I'm gonna basically, to make it easy for myself, I'm just gonna keep it roots. So it's either gonna change or not, right? If it didn't change, so parent and root are the same thing. If not, they're going to telling me that basically the root itself, right? So the current and root are the same. We didn't really change anything here. So in that case, it's going to make it easier for me to write this code. So that's what we're going to do here. We're going to now create this new node. So no matter what, we have to create this node. Which I already did it here, right? So I could just go ahead and put this whole thing on the top. Oh, not here. I'm so sorry. We're in the insert. Where's the insert method? Right here. Okay. Yeah. So this is a new node that we have here. Now we have the parent, right? So now that we have the parent, so we're going to say that if element compared to the parent, now this time, dot element, and the whole thing is going to be less than 0, and we have to add it to the left. Otherwise, we have to add it to the right. So that become parent dot left is equal to this new tree node. Or parent dot right. And we know it, it's not equal because we already returned false. We're not getting here. So when you're here, we know that it's not duplication. So here is a case of the duplication. And again, we know our parent is not null because I started with the root and I know that the root is not empty, right? So we already had all of those checking. And in this case, this is only a node, so that we're going to add it. And then when you're done with everything, we're just going to return true. So that was our insert method. So the next method we're going to add is going to be called our basically search method. So let me just kind of clean this code a little bit. So the search method also is pretty much very simple method as well, because it's very similar to these things we did here. Is going to happening inside that too. I implement the search real quick, but we have to have a print method. So for printing method, we're going to do this traversing, different kind of traversing. So we're looking for this key. And so again, we need to traverse. We either go to the left or go to the right to find a particular key. And so this part is going to be very similar to our search. Sorry, to our search for the parent, right? So it's going to be the same, the very, very similar kind of code here. For this, we don't really need to have two runners, right? Just the father, we don't care because we're not adding anything to the father. We just want to find that the current is equal to what we're looking for it or not. So we're starting from the, same thing what we had here. We're starting from the root. And then we're going to have our while loop now. And if it's not null, and I think I should make it larger from the beginning. So if it's not null, and then we keep going. So either we have to go to the left side or to the right side. So same thing we had right here. This part of the code is going to be completely similar. So if the current, element, the key here, we're using the key dot compared to the current dot element is going to be the less than 0, a negative value. Then we have to go to the left. So the current is going to become current dot left. Otherwise, we need to go to the if it's opposite. If it's positive, then we have to go to the right. And then if not, if it's equal, basically if it's 0, that means we find it. So we have to return true, and we're done with this search, and we find it. But worst case scenario for us is that we're going through this, we couldn't find anything, we get out of this. And so in that scenario, if we're getting to this point, then we have to return false. I mean, we couldn't find it. We went over all of the possibilities and was not there. So the key is not in this binary search tree.